Next up, we have Jiaoda, who will present his work on probing via prompting.
Good morning, everyone. I'm Jiaoda Li. I'm a PhD student at ETH AI Center. This is a joint work with Cotterell and Mrinmaya Sachan. So as you all know, large language models pre-trained on large text corpora can perform various tasks, including machine translation, summarization, and so on. And due to their impressive performance on these language-based models, it is natural to hypothesize that they must encode some linguistic knowledge. And one line of research that attempts to uncover the linguistic knowledge encoded in these models is called probing. So as an example, named entity recognition is one of the classical linguistic tasks. And we want to know whether the information related to NER is encoded in these pre-trained language models. And so basically NER seeks to locate the named entities in the sentence and then classify them into predefined categories. For example, there are 3 entities here. And for probing, we consider a simplified version called named entity labeling, where entity is given as an input together with the sentence the entity is in. And all we need to do is to assign a label to this entity. So traditionally, people would train a supervised model called probe on top of the pre-trained representations of this entity to predict which class it belongs to. And the high prediction accuracy is used as an indication that information related to a named entity is encoded in the representations. And we call this kind of paradigm of probing as diagnostic probing. And to help you better understand the limitations of it and to motivate our approach, I'm going to introduce an analogy here. So pre-trained language models are like corals. They are beautiful, but we don't know exactly how they work. And the probe is like the microscope we use to monitor the corals. And the learning ability of the probe is like the intensity of the illuminating light of the microscope. And the problem is if the light is too dim, then we won't be able to see many details. Just like if the probe is too simple, then just like linear models, then we won't be able to extract certain linguistic features, such as those that are not linearly separable. On the other hand, if the light is too bright, then there are some photosensitive materials in the corals that will be excited. So as a result, we won't be able to tell what the corals originally look like, because what we observe could be a result of the illuminating light. Similarly, if the probe is too complex, then the probe is capable of learning the probing task on its own, even on random representations. Then it's very hard to tease apart what the probe learns versus what the representations actually contain. So how do we solve this problem? So for the corals, the biologists find that they have some autofluorescence that can emit light. And so we can directly use the autofluorescence as a light source and get rid of the external illuminating light. But this also means we cannot use the traditional microscope anymore because the autofluorescence is not bright enough for it to work. Luckily, we have this special equipment called Fluorescence Microscope that is specifically made to generate image from the fluorescence. So in this way, we can monitor the corals non-invasively. And then back to probing, can we come up with an analogous non-invasive solution for probing? First of all, do the pre-trained language models have something similar to the autofluorescence of corals? And the answer is yes. Of course, pre-trained language models comes with a pre-trained language modeling head, which needs no extra training. And so all we need is a tool like the fluorescence microscope that can allow us to directly use the pre-trained LM head for probing without introducing an external probing model. And that tool is called prompting. So prompting is a method that adapts different tasks into the format of sentence completion so that we can directly use ML for prediction. For example, if we want to analyze the sentiment of this movie review, we want to know whether it's positive or negative, we can just construct a pattern by appending a prompt. It was blank to the movie review. There's no reason to watch a movie. And then we map the two classes into some verbalizers, such as great or terrible. And we make prediction based on which one of those verbalizers receives a higher next word probability given by the head. And we can apply the same methodology to probing, and we call it probing via prompting, or in short, BP. Again, we use named entity labeling as an example. So we can construct a pattern by concatenating the sentence with the entity that we are interested in, which is Acme Corp, followed by a blank. Then we map each different candidate category into a special verbalizer for classification. Then we make prediction based on which verbalizer receives the highest next word probability. In addition, to tell the model what task we expected it to perform, we prepend the pattern with a prefix. And the prefix can be some intuitive description of the task, like classify the name entity into the following categories, and we list all the categories. However, this kind of discrete prefixes don't work well in our preliminary experiments in the on the GPT-2. And so instead we use continuous vectors as a prefix. And the vectors are learned for each different task. And concretely, we use prefix tuning proposed by Li and Liang in 2021 for learning the vectors. So yeah, that's all for my approach. And let's move on to the experiment section. So we experimented on 5 tasks, and for the second time, I only show 3 of them here. The part of speech tagging, name entity labeling, and semantic role labeling. The prime objects of our study are a pre-trained GPT-2 and a random GPT-2. So the random one has the same architecture as the pre-trained one, but its weights are randomly reset. And because the goal of probing is to understand what linguistic knowledge is encoded in the pre-trained model, an ideal probe should perform poorly on the random one. And we say a probe is more selective than another if it performs worse on the random model. We compare with 2 diagnostic probes, one using a multi-layer perceptron and the other using a linear layer. We also introduce a majority baseline that always predicts the most frequent class in the training set. So let's first look at the random model. The dark blue bars are the majority baseline, and these 2 are the diagnostic probes. We can see both of them perform substantially better than the majority baseline. And the light blue one, the MLP, is better than the linear regression in orange. And so this shows the diagnostic probing can learn quite a lot on the probing task, even on random representations. And the more expressive the probe is, the more it learns. In contrast, our approach PP in green is barely better than the majority baseline, which means it learns much less on its own. In other words, it is more selective. Now let's see how they perform on the pre-trained model. Again, this is a majority baseline, and the 2 diagnostic probes perform quite well on pre-trained model, but it's no surprise because they are able to perform reasonably well even on random representations, as we just saw. So the question is how PP performs. Would it still be the worst of all, just like on random models? And it turns out PP is comparable or even better than the two diagnostic probes. And importantly, the fact that a more selective probe, PP, can still successfully perform these probing tasks confirms that these investigated linguistic features are indeed encoded in the pre-trained language models. So in conclusion, we propose PP that probes pre-trained language models for prompting, and it learns much less information on its own compared to the traditional way of probing. And our results confirm that pre-trained language models do learn linguistic information. And that's all for my presentation. We invite you to read our paper if you are interested. You can scan this QR code, and we also make our codes publicly available on GitHub. Thank you for listening.
We have time for a couple of questions. So I have a question to start off. So how did you come up with the specific prompt? I was wondering, and how robust, if you know, how robust were the findings to different prompting?
The prompt is very simple, just concatenates whatever we are interested in, for example, the entity and with the sentence, and that's all.
Sorry.
So, thank you for this nice work. So I think part of the motivation is getting rid of the classifier in a diagnostic probe, which has the capacity to learn something. But in the end, you use continuous tokens or continuous prompts that also have a capacity to learn something. So I wonder what you think of that. Maybe one comparison could be the number of parameters that these two have.
I think we have even more parameters than the traditional diagnostic probing. And yeah, I agree, it is also an issue that we still learn things. And so if you notice that we use the majority baseline as the lower bound, actually it's not, because if you don't learn anything, then the lower bound should be the chance, right? Mm-hmm. Instead of majority. So it is evidence that it does learn something, but compared to diagnostic probing, it learns much less.
Okay, thank you.
Thanks for the question.
Quick question. Avi Sil from IBM Research. So how would you automatically come up, or rather manually come up with the probes for more tasks? How can I scale this to hundreds of tasks that I'm working on?
You mean the probing tasks?
And just if you could speak closer to the microphone.
Yeah, I think your method, that's what I'm trying to get at.
Yeah, I think it applies to any tasks, but we only experimented on this edge probing suite that was proposed a couple of years ago. And I think it's easy to generalize to any other tasks, if that answers the question.
Okay, let's thank the speaker again. Thank you very much.